Alright, time for another DraftPhysics.com video presentation. Debate physics also, but the debate is messy. So this is a form of debate, I suppose, these DIY experiments attempting to in some way prove the existence of kinetic energy. And they're not in this, in the nice overt way where they show, for example, a 5 mass going twice the speed, creating twice as much electricity as a 10 mass going half the speed. Some, they show it taking 25 times the fuel to go 5 times faster. Some experiment like that, and instead we get this kind of stuff where they're trying to bang stuff into other stuff. So I don't think there's much reason to play this, but it does illustrate how far from recognizing all of the intricacies of doing any of these experiments and what it means when you use sticks instead of pendulum strings and different things. So I thought it would be worth going over some of that because it does apply to a previous DIY experiment done by Brozo, where we had a lever, and a spring, and he launched a 2 mass and a 1 mass from twice the distance. And the argument is that the velocity was almost twice the velocity. So, 11 frames to go a distance here, 19 frames to go the same distance here, almost 2 to 1. And the thing none of us, I guess, appreciated at that time is that this isn't an ideal lever. So even though it's a good lever, it's not ideal. It still weighs something. And its mass has to be understood as part of the experiment, and therefore it dilutes these masses. So if the lever, say, was 0.5, if it had a mass that was 0.5, you could sort of understand that this whole object would be the weight of the lever plus this, so you'd have 1.5, and that this would be 2 plus the 0.5 would be 2.5, and so you don't have a 2 to 1 relationship in the masses. And to get the 2 to 1 relationship, the easy thing to do is either remove some weight here or just add some weight here. So obviously if I made this weigh 3.0, then I have the 2 to 1 relationship back. So I just have to make this object a little bit heavier. Now what do you think would have happened if I had done if Brozo had done his experiment with the 2 mass being a little bit heavier? Maybe 0.5 heavier, maybe 0.3, doesn't really matter. Point anything, frankly, would just mean that this 19 would be more likely to be 20, and this, by comparison, would be 10, or 22, you could even say, right? It's more likely that this 2 to 1 relationship would show up, and you would get exactly twice the velocity here if you merely compensate for the weight of the lever. So this guy is doing essentially the same experiment. So we just know that we already have the Brozo experiment where it's almost showing what I would argue is the truth. And if he actually did the experiment accepting the fact that he does have to compensate for this variable of the weight of the lever, the fact that it is diluting the 2 to 1 relationship, and if he had fixed that, then it's a high likelihood that he would have gotten an answer that perfectly validates Newtonian physics. So this guy's doing this experiment. So we have these tubes, I don't know, tubes. So we have objects that weigh something, and he's putting the 2 to 1 relationship, so 1 and 2 mass, and then he's adding to the 2 mass. So I should do it this way because that's more his way he did it. So I'll just make this bigger. That's the way to do it. Even though his masses don't look, they look the same. I don't know exactly how he gets the masses right, and then he attaches the little extra bit of mass here. Now I would argue that there might be a good theory to where you attach it, because it might be that you have to consider the center of its mass. And so if I was to take this, let's say this thing did weigh 0.5, relative to these masses. So it weighs this tube weighs 0.5. You could argue, that it would be, the center of mass would be basically half of it's moving faster, half of it's moving slower, And so maybe you would want this at this location at 1/2. So you'd want to only add 1/2 the extra mass, not the full mass. So instead of adding 0.5 to this to make it 2 to 1, you'd only be adding 0.25. But that would be 0.25 here would be the same as 5 here. So you can understand that this is going twice the velocity that this is going to go at. So whatever energy you're creating with this mass, it's obviously moving at half the velocity of this mass. So it would be the same thing. So putting the whole mass half the distance would be the same as doing 1/2 the addition. But I'm not sure that 1/2 is correct, but I'm just saying that that would be, it would be logical to understand that the full mass, a 0.5 here, okay, is the same as a 0.25 here. That's the thing to understand. That those two would be the same, because this velocity would be half of this velocity. So the momentums would be the same. Now, of course, the kinetic energies would be all over the place. So, all right. So in that sense, you got a good, decent enough theory here that he's compensated for the differential, the fact that this mass is diluting the 2 to 1 relationship. And now what he's going to do, though, is a silly experiment where he's basically going to, this is the one that I would argue debunks relativity. Okay, there's no doubting that you can tell what object actually has motion when you do these experiments. So if I take this object and bang it into the 2 mass, all right, the higher velocity object, okay, and I bang it into the 2 mass, more of the energy from this object will get into this object because of that higher velocity. So this object will go further, okay, because it's going to absorb more of the energy. But if I do the experiment in the opposite way, that is, I crash the 2 mass into the 1 mass, and I'm not using a spring, okay, no spring. So the 2 mass is going to hit the 1 mass. The only velocity the 2 mass can give the 1 mass is a tiny bit more than its own velocity. So when the 1 mass leaves, if this has a velocity of, say, 5, this is going to leave with a velocity that's going to be something less than 5. All right, and this is still going to be going 4 or 3. So it's going to follow. So this one's going to leave going almost 5. Okay, so let's draw a 5 arrow that big. And this one's going to be following, okay, going the same direction with an arrow that's a little bit less. And that's exactly what happens when he does the experiment at the end of the video. So I guess maybe I'll show the end when you can just see, obviously, that less energy is transferred to the object in this case. So the heavy thing has a hard thing giving the light thing faster velocity. It really can't make it go faster. So unless I put a spring in here, all right, which absorbs the energy like a rubber ball hitting a moving car, if I throw a croquet ball at the car, the croquet ball will only go as fast as the car is going. It's not going to go much faster. It's just going to barely be going a little bit, tiny bit faster. It's like a cow catcher on a train. The cow doesn't fly off. The cow pretty much slides off. You can't really give things more velocity than the thing hitting it. So that's the problem with big things hitting little things, is they have a limit to how much velocity they can give. But if I make it a rubber ball or I make it a spring, well, then I can store the energy, and I can have half the energy go this way and half the energy go that way, so I can get it up to speed and then give it a little extra push with a little bit more of this energy. So I'll reduce this arrow, okay, and I'll increase this arrow if I use a spring. So that's where springs come in terms of creating a super elastic reaction. Not an elastic reaction, a super elastic, in the sense that they store the energy and then release it, okay, which automatically takes more energy out of the object, the heavy object. But that's not this experiment. So he doesn't have any spring in here, so he can't make this object, he can't make the light thing go twice the speed or 4 times the speed. It can only go the speed that the thing hits it. Kind of like a bowling ball hitting bowling pins. The bowling pins really can only go the speed of the ball. They can't go much faster. All right, and but the reverse, like I said, if he hits the light thing into the heavy thing, well, the heavy thing weighs way too much to take the full velocity, but it will consume a lot of the energy, okay, because it can. The fact is, it's not going to be limited by velocity. It's going to be limited by mass. So if it's really, really heavy, you can't get any velocity into it because the velocity has to be agreed upon by all the mass. All the mass has to move. So it has to be able to absorb the energy. And so if you make it too heavy, obviously this just bounces off. But the more closer these two things are to the same mass, the more of this energy will go into this. So if I make them the same mass, you know that all the energy will go in here. I make this a little bit, tiny bit heavier, well, then we know we're going to get a little bit of bounce back this way, and we're going to get a little less this way. And we're just going to keep changing that relationship. We get more and more bounce back the heavier and heavier I make this, the less energy goes into it. So we know that by making this heavier, okay, I will take less and less of the energy. But at a 2-to-1 relationship, I'm still going to get a substantial amount of this energy into this. So this won't keep going in this direction. Okay, so the light mass hits, it reflects with what energy it didn't give, and it will give the rest to this object. So it sort of proves relativity nonsense because I have two events, and if I just reverse which way they happen, the outcomes are different. They don't look the same. So the outcome of this having the velocity and this one being stationary is a different outcome than if this one has the velocity and this one is stationary. Those two outcomes won't look the same. Alright, that's probably enough. Alright, so I'll just show the end experiment because that sort of just illustrates the point that you can't do it this way. You know, you can't pretend that banging light things into heavy things is the same as banging heavy things into light things. You shouldn't expect the same outcome. The transfers don't happen as well. One experiment's more likely to transfer energy, the other experiment's more likely not to transfer the energy. All right. So you can see that in this last experiment. So for whatever reason, he decided to take the compensating extra mass off, which sort of does cheat the experiment now because now we know we don't have a 2-to-1 relationship. We've lost the 2-to-1 relationship because of the weight of these plastic tubes.
They clearly don't, do they? Clearly don't.
Oh, I gotta make sure the video is on here. You've got to be able to see it, right? Right. That would be the right thing to do, is for you to see it.
What's this?
So he's dropping the light mass from twice the velocity. I mean, not twice. It's 1.5 the velocity or something like that. All right. And obviously you can see it doesn't dramatically reflect. It actually still goes forward a little bit. So it didn't give all of its energy to the other object, but it gave a lot of it.
This.
Alright, you can see it hits. It's now pretty much stationary. Let's see, and you see it goes forward. Now watching the other case, you'll see that the heavy mass keeps going forward, which means it's going forward with a lot more energy still in it. So that's the key difference.
Nearly up to its starting point.
Doing the same thing again, we want the other direction.
Whereas this one.
Okay, so you'll see that they're almost stay together and move forward like a Newton's cradle with one ball in, two balls out kind of outcome. Both move together. So obviously the heavy mass didn't give the lighter mass much of its momentum. It didn't even give it half. It gave it something less than half just because of the weight differentials. So it gave less than half of its momentum to the other object. So it's really not a fair comparison. You shouldn't have the expectation that hitting a light thing into a heavy thing produces the same amount of transfer of energy or momentum as hitting a heavy thing with a light thing, because the transfers aren't the same. That's simple enough.
Well, you just goes about here.
That's because it can't give it a velocity it doesn't have. It doesn't have twice the velocity to give it. It can't give it twice the velocity unless you create some mechanism that allows the velocity to be converted. Unless you put it on a lever or do some other mechanism where you can convert the velocity, it can't give it twice the velocity because it doesn't have twice the velocity. It doesn't have that in its pocket. It doesn't have $10 bills. It only has $5 bills. And so they both go off together, same speed. All right, so proves my point. That's all we really need out of that. All right, so going back to the launching lever, to me that's the experiment that's still viable now that we know the simple trick, except we don't know for sure how much extra weight to put on the heavy object. But that's the way to fix the lever launching experiment. So that's what really needs to be redone, is the Brozosian launching experiment. So let me just go over that one more time for clarity. And ideally it's to find something to push where we can eliminate friction as being prejudice. It's not that you have to get rid of friction, you just have to make sure that the friction isn't prejudiced against a heavy object or a light object. Alright, so this is the real viable experiment, I guess I would say, is now that we know, we just take the mass of the lever and we understand that whatever the mass of the lever is, it has to be accounted for in the mass that we put on here. So we're going to put the 2 mass here and the 1 mass here at the right distances, and then all we have to understand is that if the lever is 0.5, okay, then it's 1.5 and this is 2.5, and to make it even we have to make this 3. And the only question is whether the 3 should be compensate for the fact that it's only half the lever. Half the lever is going fast, half the lever is going slow. And so it might be just half of this 1.5. So the right number might just be 2.75. So that's the one I'm just not sure of. But regardless, either way, whether I add 2.5 to here, 0.25, or I add 0.5, the real point is that's it. Just make this mass heavier than this one by this factor of the weight of the lever. And once you've done that, then you can leave them at these positions and get a fair contest. And I would argue that the Brozo experiment already indicates that you're going to get clearly twice the velocity here and 1 velocity here from the same force here. Same force placed in the same location here will produce twice the velocity here with something less than half the mass yeah, to compensate for the dilution created by the lever. Alright, that's enough. So certainly details I didn't have any awareness of when we got into this conversation about how levers work and everything else, because it was all based on some notion of ideal levers. So it is, again, more complicated than just these superficial outcomes to experiments. You really do have to understand all the variables.